Okay, video on year 13 binomial expansions. Last year in year 12 we looked at how to expand brackets that look like this, but we only looked at cases when n was a positive integer. And we ended up with a to the n plus nc1 a to the n minus 1 b plus nc2 a to the n minus 2 b squared, and you kept going all the way until you got to b to the n. And that's all very well and good, providing n is a positive integer. That is a full expansion. There's nothing else past that. In year 13, we look at cases like this, where n is not a positive integer. It could be a fraction, or it could be a negative number. So how do we go about doing that? Well, just consider for a minute what NCR is, what these binomial coefficients are. Okay, these NC1, NC2, these elements of Pascal's triangle that we see in the binomial expansion from year 12. Well, if we apply the original formula to this, which is n factorial over r factorial times n minus r factorial, and start to look at a pattern, then actually we can apply this choose function to non-integer n values. So let's have a look first of all. nc0, that is by definition n factorial divided by 0 factorial times n minus 0 factorial. We know that 0 factorial is 1, not 0, so we're left with n factorial over n factorial, which is 1. Okay, that's not overly interesting and hard to see a pattern, but let's keep going. If we do n factorial divided by, now it's nc1, so it's going to be 1 factorial times n minus 1 factorial. But n factorial is n times n minus 1 times n minus 2 times n minus 3 and so on. So actually the top is just n times n minus 1 factorial, and the bottom is n minus 1 factorial times 1, and we can see the n minus 1 factorials cancel, and we're left with n, which is why the second element in all of the Pascal's triangles rows are just the set of natural numbers. It's just equal to n. Okay, nc2, n factorial divided by 2 factorial times n minus 2 factorial, and we can apply the same logic here. N factorial is n times n minus 1 times n minus 2 factorial, which will cancel with the bottom. So we're going to be left with a half times n minus 1, because the n minus 2 and the rest have all disappeared. And we can do the same thing here, so that's going to be 1 over 3 factorial, because we're left with the r factorial, times n minus 1 times n minus 2, and so on. And we can start to apply these formulae, these expressions, to non-integer values of n. In general, NCR could be expressed as 1 over r factorial times n minus 1 times n minus 2. You keep timesing until you get to n minus r plus 1. Okay, so when r was 3, we stopped at 2. When r was 2, we stopped at 1. When r is r, we stop at r minus 1. Okay, so that is the general coefficient in terms of n without any factorials in it. Well, at least no factorials of n. So we can apply that to non-integer values of n. Okay, so how does that work? Well, let's first consider cases where we have 1 plus bx to the n, and in fact in this video we will only consider 1 plus something x to the power n. In the next video we'll look at what happens if this is not a 1, and we're making the explicit point that n is not an integer. Okay, so expanding this, we're going to get, well, it will be nc0, but I know n is not a positive integer, so it's not actually nc0, but it's going to be the number 1, which is the binomial coefficient, times 1 to the n, plus the next binomial coefficient, which was n, times n minus 1 of those, 1 to the n minus 1. This is why it needs to be a 1 here, because all of these then will just be the number 1. Okay, this formula will only work if that is a 1. And then we have a bx, bx to the 1, plus, and then the next binomial coefficient would be n times n minus 1 over 2 factorial, times 1 to the n minus 2, times bx squared, plus n times n minus 1 times n minus 2 all over 3 factorial as the binomial coefficient, times 1 to the n minus 3 times bx cubed. And you can keep going as long as you like, as long as it's necessary, but it won't stop. If n is not a positive integer, these won't stop. If n was a positive integer, then eventually these binomial coefficients would be 0, which is exactly what we see in the Pascal's triangle. Eventually they turn to zeros because you eventually catch up, n will catch up with whatever, these brackets will catch up with whatever n is. But if n is not a positive integer, then the top will never be 0, which means the binomial coefficients will never be 0, which means these terms don't finish. So this will give you a polynomial of infinite degree, okay, which technically isn't a polynomial. But that's okay, because what we can do is we can limit what bx equals. So we can say this is valid if and only if the modulus of bx is less than 1. Because if the modulus of bx is less than 1, then as you increase the powers of bx, these terms are going to get smaller and smaller and smaller. But if bx is bigger than 1, or if bx is less than minus 1, then these terms are going to get bigger and bigger and bigger, and then it's not going to be a reliable estimation because you need an infinite number of terms, which isn't possible. So we have this kind of extra restriction in place. The modulus of bx must be less than 1, or if you like, another way to write it, minus 1 is less than bx is less than 1. This is a bit more mathematically rigorous because it's true for complex numbers as well, but on this course we don't actually apply this to complex numbers, so this is sufficient. Okay, so that's the general theory. In the formula book for Edexcel, at least, we have what this looks like. So we can see where n is a real number, okay, so not necessarily a positive integer now. Modulus of x is less than 1. You are given that 1 plus x to the n is equal to 1 plus nx plus n times n minus 1 over 1 times 2. So that's the binomial coefficient times x squared. And then it gives you the general term here. Okay. Usually a question will ask for up to the cubic term, and that's because it gives you the constant, the linear and the quadratic, so you need to use this general one to get the cubic, so it's testing that you can apply r is 3 into here. Okay. All right, let's have a look at some examples. Okay, example number 1. Expand 1 plus 2x to the power of a half up to and including the cubic term. So we know that the formula in the formula book says 1 plus, I'm going to put it as a capital X, 1 plus something to the power n. That is roughly, and it is an approximation, 1 plus nx plus n times n minus 1 over 2 factorial x squared plus n minus 1, n minus 2 over 3 factorial, and then there'll be an x cubed, but I've run out of space on the page. So we're given the first 3 terms in the binomial, in the formula booklet, and the next one you can extrapolate further. So you include the n minus 2 on the top, and you up that to a 3 factorial. And you could see that this is actually over 1 factorial, and that is over 0 factorial, but they're just not included because those two are both a number 1 anyway. So the pattern does continue as you go up the chain. Okay. So applying that to this, n in this case is the number half, because that is the power, and the capital X in this case is going to be 2x, because that's what is adding to the number 1 inside the bracket. So we can put these in. So we're going to get the number 1. It's always the number 1, because it's always the number 1 here, plus nx. So n is a half, and x is 2x. Okay, capital X. This thing is 2x. Plus n times n minus 1. So n is a half. N minus 1 is minus a half, divided by 2 factorial times x squared, so that's 2x squared. Okay, just be careful, the most common mistake is not to bring the whole thing in. Plus n times n minus 1, which is minus a half, times n minus 2 now, which is minus 3 halves, divided by 3 factorial times 2x cubed. And we only want to go as far as the cubic term because that's all the question is asked, but the question question would, the expansion would continue indefinitely. Okay, so let's simplify these terms. We're going to get 1. A half times 2 is just the number 1, so it's just x. Then we got a half times minus a half divided by 2. So altogether that gives you minus an eighth, is the binomial coefficient there. But we're going to times that by 2 squared. So it's going to be minus a half, so minus a half x squared. And then this one here, I'm actually going to crack the calculator out for just in case I make a mistake. Let's delete all of that. So we're going to get a half times minus a half times minus 3 halves times 8, because that's what 2 cubed is, divided by 3 factorial, which is 6. And that gives me 7, 6, oh, that's not right. 3 halves is 1.5. Yeah, positive half. So that coefficient there is positive a half x cubed. And that's as far as we want to go, because we're told to go as far as the cubic term. Okay. For these expansions, we should also restrict what x should be. So in this case, don't forget we said that capital X needs to be less than 1, and modulus of capital X needs to be less than 1. In this case, the modulus of 2x is less than 1. So that implies that the modulus of x is less than a half. In other words, this is only valid for x values between minus a half and a half. It is not valid outside of this range. Okay, either one of those, so either the top definition or the bottom definition. Okay, 2 more examples to go. Sometimes you'll need to extract what the value of n is. In this case, 1 over 1 minus x. You need to know that this is equivalent to 1 minus x to the power minus 1. So in this case, in the formula, n is going to be the number minus 1, and what was a capital X at the top of my page is equal to minus x. So I'm just going to plug these 2 definitions into the formula at the top of the page. I know you can't see it, but it is 1, always the number 1, plus nx, so it's that times that, which is x, plus n times n minus 1 divided by 2 factorial times x squared, plus n times n minus 1 times n minus 2 divided by 3 factorial times x cubed. And we can keep going, but we only want up to the cubic term. So that's going to be 1 plus x, and in this case, the 2 on the top and the 2 on the bottom will cancel, and the minus x all squared will just give you positive x squared, so it's just plus x squared. And then this one, again, the 3 factorial on the top will cancel with the 3 factorial on the bottom, leaving just a negative 1. But minus x cubed is minus x cubed, so that actually is positive x cubed. And if you expand this further, this is actually just plus x to the 4, plus x to the 5, plus x to the 6, plus x to the 7, and so on. There we go, that's it. For those of you who have studied geometric sequences, then this is a geometric sequence, and if you apply to the sum to infinity formula on it, you will actually get back to this. All right, that's the sum to infinity formula for this geometric series. Okay. All right, and finally, example number 3. Sometimes you're given an extra little multiplier as well in this. Oh, actually, sorry, apologies. I didn't restrict what values of x I need. The modulus of negative x needs to be less than 1, which is the same thing as saying the modulus of x is less than 1. Or if you like, minus 1 is less than x is less than 1. Okay, that's it. Apologies. Right. Example number 3, yeah, sometimes you're given an extra multiplier. So in this case, we're just going to apply the binomial expansion to the denominator. So I'm going to say that the denominator is 1 plus 2x to the power of negative a half, okay, because it's the square root, so it's a half, and it's on the bottom, so it's negative. And the formula, don't forget, is 1 plus nx plus n times n minus 1 on 2 factorial x squared plus n times n minus 1 times n minus 2 on 3 factorial x cubed. Okay, and so on. So we're going to apply that here. In this case, our n is minus a half, and our capital X is 2x again. And we're just going to take these two definitions and plug them into the first 4 terms up here. So we get that this bracket, and only this bracket, we're ignoring the 2 plus x for now, this bracket is equivalent to 1 plus nx, so that's minus a half times 2x is minus x, plus n times n minus 1 over 2 factorial times 2x squared plus n times n minus 1 times n minus 2 over 3 factorial times 2x cubed plus dot dot. Okay, so the first term is 1 minus an x. Again, I'm going to get my calculator out because it's easy to make a mistake on these. So minus a half times minus 1.5 times 4, because I get the 2 squared from the inside the bracket there, and that's divided by the number 2, because that's what 2 factorial is. So I get 3 halves. So plus 1.5x squared, and then finally we're going to get, in fact I'm just going to modify this one up here, minus 2.5 times minus 2.5. Now it's going to be times 8, because we're going to have 2 cubed this time, and the denominator is going to be 3 factorial, which is 6. 3 times 2 times 1. Oops. No, yeah. Sorry, syntax error, because I've got a fraction down there. So that's minus 2.5x cubed, and that's as far as I need to go. That's obviously just the denominator. Recall that 2 plus x over the square root of 1 plus 2x is exactly the same as 2 plus x into 1 plus 2x to the power negative a half. Okay, that's exactly the same thing, but I've got an expansion for this up to the cubic term. So I'm going to say this is approximately 2 plus x times 1 minus x plus 1.5x squared plus, minus 2.5x cubed, and that would carry on, be quartic term, quintic term, etc. And now just expand the brackets. So the constant is going to come from the constant times the constant, so 2 times 1 is 2. The linear term is going to come from the constant times the linear, and the linear times the constant. So I've got minus 2x plus x is minus x. The quadratic term is going to come from the constant times the quadratic, and the linear times the linear. So I'm going to get positive 3x squared minus x squared leaves me with plus 2x squared. And finally, the cubic term is going to come from the constant times the cubic, and the linear times the quadratic. So I'm going to get minus 5 plus 1.5, which is minus 3.5x cubed. And stop there. Okay, dot, dot, dot. There will be more terms in the infinite expansion, but we only asked to go as far as the cubic term. So we stopped there, and we ignore the fact that we're going to get a quartic. So the x times the minus 2x cubed, that would actually give a quartic term, but we ignore that because we've ignored the quartic term, which would occur from the quartic here times the constant here. So we haven't got that in the bracket because we weren't asked for that. So we ignore it from this expansion. We don't put the plus or the minus 2.5x for 4. That's not part of it. We stop at the cubic term. And the final thing left to do is just to decide what the restriction on x is. So there's no restriction on the top because that's just a linear, that wasn't a binomial expansion. The bottom one is a binomial expansion with non-integer n, so we need the modulus of 2x to be less than 1, which means that x must lie between minus a half and a half. And that's the restriction. That expansion is only valid for those values of x. If it's less than minus a half, then actually you can't plug it in anyway because you'd be square rooting a negative number. And if it's bigger than a half, then this is just too far away to be a valid approximation. Okay, so that's the introduction to the binomial expansions. The next video we'll have a look at what happens when the first number inside the bracket is not the number 1. And then I think I have a third video as well, which will look at some problems. Okay, thanks for watching. I hope you found this useful.